Hi everybody. Today we're going to do some RC circuit examples. I'm Michelle Maharbaz.
And I'm Vivek Subramanian. Let's get started. So in the last module we talked about the basic equations that we use for RC circuits. We're going to apply them here. So before we do, if you're just starting this module up, one thing I would recommend is go ahead and review those equations. Just make sure you have those equations in front of you, because we're not going to derive them here, but we will use them. And what we'll try to do is explain circuits qualitatively, and then we'll apply the equations to solve them. So it's to your advantage to make sure you have those equations in front of you and you sort of recognize them. So let's move on to our first example. The first example is the circuit shown on the top over here. This is the circuit we're going to analyze. And specifically, you'll recognize that it has a capacitor right over here, and it has various resistors, but specifically there's one equivalent resistor associated with the capacitor, so we can treat this as a RC circuit and analyze it as such. And there's a switch in here, and the switch is going to change from position 1 to position 2. Now in position 1, you see that there's a source over here, and in position 2, there's also a source over here. So Michelle, does this remind you of a particular type of response?
Yeah, my guess is that after the switch closes, we're going to be looking at a forced response in the solution.
That's right, because in position 2, which is where the switch is closed, there's still a source in there, so it is a forced response solution. Okay, so let's go ahead and do this. Now you'll remember how to do this. Let's do it qualitatively first. What you do is you figure out how the circuit was at the condition prior to the switching event, which we call t is equal to 0 minus. So that's pretty easy. We ignore the right-hand side of the circuit, and all we're left with is the left-hand side of the circuit. In the situation where it's been sitting in configuration 1 for essentially forever, we can model the capacitor as an open, and we can use that to analyze the circuit. And specifically what we work out is we work out what the circuit looks like. You'll recognize that this is basically a voltage divider, so we can then calculate the voltage that the capacitor charges to, and it turns out it's going to be 30 volts. We'll show you the math again when I work through the actual equations, but recognize this is what we're going to do.
So another way to think about this is you could take the 45 volt voltage source and the 4 kilo ohm resistor, convert that to its equivalent current source plus 4 kilo ohm resistor in parallel, collapse them, and then reconvert them to a voltage source and a resistor, and that would be the Thevenin equivalent of everything to the left. That's the easiest thing to do, because after all, you just care about the equivalent source and resistance with respect to the capacitor.
That's right. And by this point, you should hopefully be familiar with source transformation as well as with doing these sort of resistive circuit analyses. Okay, now that's what happens up to the switching event. Right after the switching event, namely at t greater than 0, what happens is the switch has moved to position 2. And now at this point, we only care about the right-hand side of the circuit, so that's shown right over here. Again, we can simplify the circuit, taking advantage of Thevenin equivalent circuits and resistive simplification. And now what we end up with is this circuit over here. And what we're going to do then is we're going to essentially analyze this circuit. If you look at this one, this looks very much like the forced response of an RC. So that's the equation framework that we're going to use. Okay, so that's basically how we're going to do it. So I'll go ahead and remind you again. We're first going to figure out the DC response, and that's going to be done using a Thevenin equivalent. The capacitor gets charged up to that, and then we look at the forced response once the switching event takes place. So let's go ahead and do that now. All right, so here's the solution. So initially, we charge the capacitor. When we're in position 1, we're charging the capacitor up. So we can calculate at time is equal to 0 what the specifically at time is equal to 0 minus what the capacitor charges to, and that's 30 volts. Again, we make the assumption that because of the fact that capacitors fight against abrupt changes in voltage, the voltage at V is equal to 0 will be equal to V is equal to 0 minus. So therefore, we'll say that's 30 volts.
So, okay, so what you're saying is that circuit on the left has been sitting there forever. Because it's sitting there forever, we can model the fully charged up capacitor as an open. And because it's an open, we know that just looking at that circuit, and if you want, you could do KVL, but just looking at it, you know that that capacitor is going to have 30 volts across it. And so that gives us the voltage at t equals 0 right before we begin to generate the solution for the right-hand side of the circuit.
That's exactly right. So it's at 30 volts at time 0 minus, And because of the nature of capacitance fighting abrupt changes in voltage, that will also be the voltage at time is equal to 0. Then, because we're solving a forced response solution, we recognize that the right-hand side of the circuit is a forced response solution, so it's going to fit to this equation form. Now, this is where I encourage you to go back and review how we came to this equation, just to make sure you know it, but you will in fact recognize this is a forced response solution. What we need to solve this problem is we need three things. We need V at infinity, V at 0, and tau. Okay? So V at 0 we've just calculated to be 30 volts. V at infinity we can calculate as well, right? Because this circuit we can essentially analyze what will happen when the system has been sitting in this configuration forever. And you know, again, from the representation of this circuit, when this has been sitting forever, what do you think the voltage on this capacitor is going to be intuitively, Michelle?
Well, it's no current's going to run through the 10K resistor, so it's going to be exactly what we did for the original condition with a different circuit. It's basically just going to be that voltage, 20 volts. It's going to drop entirely across that.
That's right. What happens is this system is going to equilibrate till the point where the 20 volts is available on the capacitor. And
I'd like to point out what Vivek sort of told you we were going to do. If you look at the expression here for V infinity, what we've done is worked out the Thevenin equivalent for the circuit on the previous slide.
Yeah, so you can see that here. We took this circuit over here, and this Thevenin equivalent shown over here is what we calculate over here.
Right, so that's how you calculate the Thevenin equivalent voltage, and then the Thevenin equivalent resistance is just below it, just so you wonder what those numbers are.
Right. So what we have is 20 volts, and we have the 10 kilo ohm resistor value, and so then you know at time is equal to infinity, this capacitor should charge up to 20 volts.
Perfect.
Okay, so we now have V0 and we have V infinity. The last thing we need is tau. Well, the Thevenin resistance gives us that as well, because you recognize this is a RC circuit. We know the value of C. The Thevenin resistance gives us the value of R. We use those to calculate tau, and we've got the value of tau as 0.2 seconds. So now we can drop those into this equation, and we get our final solution. And our final solution is the forced response of this solution, and specifically you'll recognize that this has taken in all the values we needed to do our calculation. In other words, it's starting at 30 volts, and then it ends up at 20 volts, and in between it drops off following the form of this equation, which is the forced response.
And note again, just like we said in the last module we told you about, note the complete solution has a term that doesn't change with time. That's going to be the term that's left behind. After this term, which is sort of a transient, decays out. So as time progresses, this gets smaller and smaller, eventually goes to 0, and you're left with what you expect, which is the steady state solution is the capacitor is sitting there at 20 volts. So very briefly, when you look at this problem, now having worked through it, what we did was we knew that it sat at the left side forever, and at t0 it went to the right side. So all the time-dependent stuff happens after t equals 0, right? That's where we work out all of this v of t stuff. We used the left-hand side of the circuit, which its only purpose was to set the initial condition for this capacitor. That's just to make it very clear. The whole point of the left side was just to come up with a complicated way of asking you to solve for the initial condition of the capacitor. And then all the real interesting stuff happens when the switch switches, then that pre-charged capacitor at 30 volts goes through its paces. Fair enough?
Makes sense.
Okay, let's try another one. So this one here is a switch that's going to go through two motions. So this is the figure we have, right? So you see a voltage source, you see one capacitor, two resistors, and a switch that can be in either position 1 or position 2. So it starts out at position 1, and it's been there for a long time, and then it switches to position 2 at t equals 0. But then at t equals 10 seconds, we're going to pop it back into position 1. So what do you think, Vivek? Is this going to be forced or natural response?
Well, my guess is we're actually going to have a combination, because there's two switching events. If I look at the first switching event, there's a voltage source in there, so there's going to be a forcing function. But then when I bring it back again, now it's just the capacitor that's going to discharge, so I will get a natural response out of it.
That's exactly right. And so the trick here is we're really going to do almost two problems. They're going to connect to each other, obviously, but the trick is to break it up into two segments and solve each segment independently following the rules we've given you. Okay, so let me go through that. So we know that it's been sitting at position 1 for all time, and at t0 it's going to pop up to position 2. Okay?
So if it's been sitting at position 1 for all time, I guess I know the value on the capacitor. It should be fully discharged.
Right. Since there's no source in that configuration, you know that if you waited long enough, this went to 0. That's exactly right. And we're going to use that fact in a minute because that gives us the initial voltage on the capacitor. So looking at it after it switches, just immediately after it switches, it's got this configuration. And it's going to stay in this configuration between 0 and 10 seconds. So when we solve this first part of it, we're going to use this circuit. This is the configuration it's in. Okay?
I see. I think I understand. So what you're saying is that those equations that we developed in the last module were, for example, the forced response and natural response were to go all the way to t is equal to infinity. I'm going to use them, but I'm going to cut them off at the 10-second point and sort of recalculate what happens.
Yeah, exactly. The circuit doesn't know you're going to switch it later.
Right.
So you're going to solve it naively as though it was always going to be this way, and then we'll show you how you transition between the two solutions, which is pretty easy. So for the first part, you switch the circuit into this configuration. Well, you just have two resistors in series, which is the same as one resistor that's the sum of the two. So our tau for this situation is just R1 plus R2 times C, right? It's just a simple RC circuit. You can figure out what that number is from the values up here. And if we want to know what the time-dependent, what the evolution of this voltage V1 on the capacitor is going to be, we're going to adopt the same form we've been using. That is to say, we need the value of the capacitor voltage at infinity, assuming nothing else happens, right? So again, the circuit doesn't know we're going to change at 10. And then the initial value and tau. So we've got tau. Right. What do you think the other two things are?
Well, the value at infinity is pretty straightforward because that V1 is the problem tells me it's a 20-volt source.
That's right.
So I know if I waited to infinity, ultimately that capacitor would end up at V1.
That's exactly right.
And at 0, if I look at that system, well, it was discharged to begin with, so it should start at 0.
That's right. And if you plug that in, you'll find you put 20 here and 0 minus 20 e to the minus t over 25 seconds. You'll clean it up and you'll get this expression. So this is the form of the voltage. This is exactly what the voltage is doing as a function of time in the first 10 seconds. And that's what it's going to do. Again, there's no look ahead. The circuit can't look ahead to see what's going to come next. So this is what it's doing. Now, at 10 seconds, we switch it back from this position here to this one. So it goes back to being in this configuration. So do you think this solution is going to have a forced or just a purely natural solution?
Well, I don't see any voltage sources here, so as I told you earlier, I suspect this will be a natural response.
Exactly. This is all that's going to happen now is that this capacitor is going to discharge to this resistor until it hits 0. Okay? So going through that explicitly, now we're at t greater than 10 seconds. We're gonna be formal and basically write it all out. So we're gonna write out the whole expression again. And remember now, we're going to write out this expression and time shift it by 10 because this is the part of the expression that deals with t after 10, right? So we know that we're going to time shift this exponential by 10 seconds, and this won't be v2 of 0, it's v2 at 10, right?
I understand, and you're doing this because this new switching event is at 10 seconds.
That's right, that's exactly right.
Okay.
So now we're going to fill in the blanks as we did before. For the new circuit, here it is again, the time constant for that circuit, in other words, for the circuit after it switches at 10, is just R2 times C. So we write that down. We've got a 5-second tau that's going to go here. And then the initial condition of the circuit, this is the only little fun part. What is the voltage of the capacitor at 10 seconds?
Well, I'm going to take a guess here. Since I again assume that capacitors abhor sudden changes in voltage, I will assume that it's going to be at the voltage it was in this configuration at time to 10 seconds.
That's right. So that's exactly right. The capacitor can't change voltage instantaneously, which means that when we flip the switch from this configuration to this, whatever value it had at that instant, it's going to have at the beginning of our segment 2. And so we go back to our previous equation here, and we just plug in 10 seconds. We ask at 10 seconds, what was the value of this V1? So 20 times 1 minus e to the minus 0.04 times 10 seconds. Plug that into here. And you get that it just so happened that it had charged up to about 6.5 or exactly 6.59 volts. And we know that's the initial condition for the capacitor in the second part. And then what is it going to be at infinity? We both just said this is natural, so it's going to be 0, right? This thing is just going to discharge at 0. So plugging in a 0 here and a 0 there, we'll get the final form of this, which is 6.59 e to the minus 0.2, t minus 10 sort of shifted by 10. And that's essentially the complete solution for this, that we did it piecemeal. For between 0 and 10 seconds, it has the form given by V1, and between 10 seconds and infinity, it's got this form here. Now we're going to do another problem that Vivek's going to take over and do, where we actually, by superposition, break up, instead of doing it time segmented this way, we're going to do it by superposition, and you'll get a complete expression. So let's show you how that works.
Okay. Now the way to do that is we're going to, instead of having a switch moving, we're going to consider a circuit where we're using a pulse on the voltage source. Now you'll remember from the section on non-periodic waveforms or time-varying waveforms, we talked about a pulse. Michelle, could you think how we could decompose this into simpler parts?
So I've got a pulse. That pulse can be broken up by superposition into two step functions.
Yep.
The first step function is going to switch from 0 to Vs at 0, so that must just be Vs times the step function u of t.
Correct.
And then that would stay at that level 10, and if I wanted to bring it down, I have to subtract out a step function that is time shifted. It's got an amplitude of Vs, so it comes down to 0 from Vs, and it's time shifted so that it switches at 4.
That's
and
right.
So this expression here recaptures the rectangular pulse, but it allows us to have two terms that are both step functions.
That's exactly right. Now, the beauty of this is this circuit is linear. It has a resistor, a capacitor, and a simple source. So we can then split this up and use superposition to solve it. In other words, we can break this into a problem where we first deal with the rising step function, figure out what the response is, then deal with the falling function, which is time shifted, figure out what the response is, add them up, and we'll get the overall function.
And that's essentially what we did. In the last example, we just sort of did it with switches and kind of broke it up, but here you're doing formally.
That's right.
That's great. Okay.
So let's go ahead and do it. It's pretty straightforward. We'll deal with that first step. The first step is the equation for V1, namely that rising step function. So again, the form is the same. We figure out what was happening at V1, 0. And in that configuration, of course, we assume it's been sitting there forever. So Michelle, what would the capacitor voltage be at V1, 0?
Well, so the independent source would have been at 0 for all time. So the capacitor would have gone to 0. So V1 of 0 is 0.
Correct. And then V1 at infinity, of course, we would assume that the capacitor charges up to the full 10 volts.
So it's
and
10.
then correct. And then we can calculate tau from RC, which we have over here. We plug those all in, and we get the equation for V1. Pretty straightforward. We do the same thing for V2. Now remember, this is time offset. So instead of evaluating as we do here for a time of 0 and minus t over tau, we evaluate at a time of 4 seconds, and t minus 4 goes into the numerator of our exponential. But in all other ways, it's basically the same, because now what we're doing is we're going to figure out what happens for a falling edge. Now, this is where it's a little different than the way Michelle dealt with the last problem. In the last problem, what Michelle did was he figured out at that crossover point what was the initial voltage. This time we're not going to do that. We're going to use V2, where V2 is just a time-shifted downward pulse or a downward step. Okay?
Got it.
So we don't have to now calculate what it was at that instant. We're going to say it's been sitting at the positive level at 10 volts for all eternity. So that means at the initial response point, the capacitor would have been charged to 10 volts. Exactly. Okay? And then, of course, at infinity, it fully discharges. So we plug those in, and we get the V2 response. Now, by superposition, we put them together by adding them. So the total system response, V, is going to be the sum of V1 and V2. So we add them together, and we get an equation for V. Now we can plot that, and when we plot that, what we see is it is indeed a combination of these two. We have the force response, which does that, and we have the natural response, which does that.
That makes sense. So the difference really with the last example is that in the last example, we had two solutions that each only held for that particular segment. So I had a solution for the voltage, the total voltage between 0 and 10 for the last example, and 10 and infinity. Here, we actually, as exactly as you laid out, we have a VFT expression that holds for basically all of time. And it's because we did this addition of time-shifted stuff.
Correct. Now, one thing that's worth noting is to account for the fact that it's time-shifted, we essentially have to include the step function shifted with respect to time. Otherwise, if you were just to add the natural response obviously it would be sitting at 10 volts for all eternity to that point. So we need to put in a step correction such that it only shows up at that point.
Basically, the second term is 0 until t minus 4. U of t minus 4 is 0 until 4, and so that right term on the right of the minus sign is 0 until that time.
That's right. That's how we get this.
Cool.
So this is how you see. Now, this is a good example to show you how superposition can make your life easier in terms of the analysis, because we didn't have to figure out what the value was at that step time.
Right. Cool. Very cool. All right. There's two other circuits we want to show you that are pretty neat, since you all know op-amps now, that just involve adding capacitors into either the feedback loop or the input component of a op-amp, simple op-amp circuit. We're just going to do two. There's an infinite variety of these kind of things, and in analog circuits you run into a lot more combinations that have useful purposes, but these are fairly straightforward. So let's take a look at this. All we've done here is we took a straightforward inverting amplifier, and instead of having a resistor here and a resistor here, usually called RF, we shoved a capacitor in the feedback path. And it does some interesting stuff. So I'm going to walk you through sort of quickly skim through an analysis of this, because it should be relatively straightforward. So first of all, recall that there's no current going into either the inverting or the non-inverting terminals of our ideal amplifier. And moreover, that the Vn and Vp potentials are the same. So Vn equals Vp, which, because Vp is at ground, means Vn is at ground.
And that's because we have negative feedback.
That's only because we have negative feedback. That's exactly right. So given these conditions, this current IR is Vi minus the potential here, which is ground, over R. That's what you see there. Okay? Now, the drop across the capacitor is V out minus 0. So that's the voltage across the capacitor is essentially V out, right? Because the other side is 0. And so we know from the capacitor equation that the current going into this positive terminal of the capacitor IC, I equals C dV dt. So IC must equal C times dV out dt, because V out is the voltage across the capacitor. Okay? Now, KCL tells us that at this node, IR, IN, and IC must obey KCL. So IR plus IC minus IN equals 0. But we also know IN is 0, which quickly tells us that IR plus IC equals 0, or this expression here. And now we have expressions for both of those. We know that IR is VI over R. We know that IC is C dV L dt. We have it this way. We clean it up a little bit. And now notice the derivative of the output is the input times some thing basically multiplied by an RC time constant. So what we do is we integrate both sides to get an expression for V out. This is easy. Just take the integral of the left. That gives you V out. Take the integral of the right. RC doesn't get integrated because it doesn't change. And so you get that the output voltage is minus 1 over RC. This is this constant that comes from the circuit, times the time integral of the voltage over some period that you care about, plus whatever the voltage was before you started caring about it, before you started integrating.
Makes sense. Now, these kinds of circuits, I mean, it's a cool mathematical concept. It looks like what you've got is a circuit that's performing a mathematical function. It's integrating.
Well, back in the day when vacuum tubes were popular and before the rise of digital computers, people in fact did perform some calculations with these types of analog circuits. But there are other uses for these, and Vivek is kind of an expert on some of these. And so what do people use them for?
That's right. So it turns out one of the biggest uses for these is in applications where we are essentially trying to sum up numbers. And the specific application where this is used is to count charge. Because if you think about this, we use these, if we have a current flowing into an integrator, and we're integrating current with respect to time, what we end up getting is a sum of all the charge that flowed into that node.
I get it. So basically it's a way of measuring how much charge has moved into, essentially in the direction of that op-amp or through the op-amp, into the op-amp. That's
right. So it's used in a lot of applications that require sensing current, or counting current over time. So a lot of sensing application, user interface circuitry, things like that, use these sorts of systems.
These sort of front ends. That's cool.
Correct.
That's very cool. Okay. Well, let's look at a complementary case very quickly, which is the ideal differentiator. You want to take this over?
Sure. So the differentiator we can move pretty quickly because now what we've done is we basically switched the locations. We've put the capacitor on the input and put the resistor on the feedback path. We can again calculate IC as C dVi dt. It's dVi dt because we assume an ideal op-amp in a feedback, negative feedback configuration, so Vn is grounded. So we have this equation. IR is easy to calculate. It's just V out over R because, again, Vn sits at 0. We know that IC must equal to IR since we assume that there's no current flow into and out of the inputs of the op-amp. So we can again integrate, or in this case we can arrange it, and actually we end up calculating V out as a differential, where we get V out is equal to minus RC dVi dt. If we wanted to find the input with respect to the output, it would be an integral, but if we find the output with respect to an input, this is now a differential. So we call this an ideal differentiator, because what this does is this takes an input and it calculates its differential. So this is the complement to the integrator. Any idea what we use these for, Michel?
Well, what this must be very good at is looking for changes. So anytime there's a big change in the input voltage, so maybe like a switching event?
Yep, that's right, because remember, when you have a discontinuity, the integral jumps. So this thing will show a little pulse every time that happens.
That's great. All right, well, we hope this module has been useful in kind of going just through the mechanics of how you solve some of these first-order RC circuits. And we'll see you pretty soon as we kind of continue to plow through this sort of time domain stuff. Thanks a lot.